Yeah, this is Dr. Vamsi Mohan, Professor, Department of Civil Engineering, Institute of Aeronautical Engineering. And today's topic is about section modulus of various cross sections. So, in the previous session, we have discussed about the bending equation given as m by I equal to f by y equal to e by r. Okay, so which is derived based on the bending curve as shown in this figure. So here from the bending equation we can have this relation as sigma is equal to m by I into y, where sigma is the stress at any section, at any layer at a distance y above the neutral axis. So if you consider a layer here at a distance y from neutral layer, this is neutral layer or neutral axis. So at the distance y, the stress in that fiber is given as m by I into y. So from this it is clear from this equation that sigma is directly proportional to y, because for the given loading and cross section of the beam, m by I will be constant. M by I will be constant. So sigma is proportional to distance of fiber from the neutral layer. It means the stress across the section varies linearly with distance from neutral axis. And at the neutral axis, already it is seen that the stress will be zero, because one side of neutral layer, the fibers are in compression, and on the other side the fibers will be under tension. Okay, that means there will be some layer which is neither subjected to compression nor to tension. That layer is said to be the neutral layer, and the line of intersection of this neutral layer with the cross section, if this is the beam lengthwise, you can observe. Okay, yeah, neutral layer will be somewhere here at the middle, or depending upon the position of centroid actually. Okay, yeah, this line is the line of intersection of neutral layer with cross section, and that line of intersection of this neutral layer with cross section is said to be the neutral axis. Okay, that is shown here in this figure. Okay, which passes through the centroid of the section, Okay, so at the neutral axis the stress will be zero, because the distance is measured from neutral layer. The distance of fibers is measured from neutral axis. So at the neutral axis the distance is zero, and hence the stress will be zero. As per this equation, the stress will be zero at neutral axis. Okay, and it will be maximum at the extreme fibers, because the distance of fibers is maximum at the topmost or bottommost fibers of the cross section. Okay, so here if it is symmetrical, then the distance of topmost and bottommost fibers will be the same as in this case. If it is rectangle, then distance of fiber will be d by 2 from neutral axis at the top and bottom also. But if the section is unsymmetrical, for example, if you consider a T section, something like this. Then the section is unsymmetrical. So neutral axis lies somewhere here. Okay. So here the stress will be 0 at the neutral axis, not at the mid height. It will be 0 at the neutral axis and maximum at extreme fibers. And here the distance of bottom fiber is the maximum compared to the top fiber. The distance from bottommost fiber is greater. So the stress will be maximum at bottom fiber. Okay. Of these two, the stress at bottommost fiber is greater. Okay. So maximum stress now occurs at bottommost fiber. Okay. This being maximum because distance of bottommost fiber is greater than that of the topmost fiber. Okay. So the stress will be maximum at the bottommost fiber. It is clear. So here, while calculating maximum stress, we will take m by I is constant. So we have to take maximum distance from the neutral axis. Okay. So maximum distance means the greater of the distance of topmost fiber and distance of bottommost fiber. Greater of these two will be the maximum distance that we have to consider here to find maximum stress in the beam section. Okay, it is clear. So now, based on this equation, we express the bending moment in terms of maximum shear stress. That equation is given something like this. Yeah, m is equal to I by y maximum into sigma maximum. Okay, I by y maximum into sigma maximum. So this gives the moment of resistance of the section, cross section, given cross section. Okay, resisting moment which opposes the moment due to external loads. Okay, so here this term I by y maximum is said to be the section modulus for the given cross section. Section modulus for the given cross section. Okay, so different cross sections will have different section moduli. We will see one by one cross section how to find the section modulus of each of these cross sections. Okay, so here I is second moment of area or moment of inertia for the given cross section. Okay, and y maximum is distance of the extreme fiber, either the bottommost or topmost, whichever is at larger distance from the neutral axis, that will be considered as y maximum. Okay, now this is denoted by letter z. Okay, so m is given as z into sigma maximum, z into sigma maximum. So in other words, we can say that z is a measure of the bending strength. The section modulus is a measure of the bending strength of the given beam. Okay, so it is an important parameter, the section modulus. So finding it for different cross sections will be of importance in finding out the bending strength of the given cross section. Okay, so now let us see sections. Already this we have seen. In the last session we have discussed about it. Okay, so neutral axis, location of neutral axis is important. Okay, because for the given cross section we need to first locate the neutral axis which passes through the centroid. Okay, yeah, that is clear from this equation actually. Okay, so for sigma dA means, what is sigma dA actually? Moment of force actually. Sigma dA is force on this elementary string. Force on this elementary string. So the total force is obtained by integrating this between the limits of y. Between the limits of y. Okay? By integrating this between the limits of y, we will get the total force parallel to the axis of the P. And also we know that for equilibrium, the resultant force must be 0. Okay? Understand? For horizontal equilibrium, the resultant force on the cross section must be 0. So, this must be 0. And as there is no external force, the entire force is due to the internal stresses. Okay? That is integral sigma dA is resultant force acting on the cross section. Okay? That means you will have compressive force on one side in case of cantilever. Which bends downwards, you will have compressive force below and tensile force above. So on this area you will have tensile force and on this area you will have compressive force. So the net force must be 0. T minus C is equal to 0. Minus C because it is in the opposite direction. Okay, compressive force is in the opposite direction to that of tensile force. So the net force must be 0 or T must be equal to C. So the total compressive force acting on the bottom area below the neutral axis must be equal to the total tensile force acting on the area above neutral axis. Okay, that is the net force sigma dA, integral of sigma dA must be 0. So that is for equilibrium, we know that. Okay, so what this says, what do you understand from this equation is the compressive force must exactly balance the tensile force. Compressive force must balance the tensile force. Okay. So sigma can be replaced as E by R into Y. From bending equation, we know that sigma by Y is equal to E by R. So from this, we can replace sigma here in this equation by E by R into Y. Okay. So this equation now will be written like this, E by R into Y. And also is known that E and R are constants for the given loading and material of the beam. Okay. E is material property actually, Young's modulus. So it is a constant. And R, radius of the curve, which depends on the loading. Okay. As the load increases, radius also changes. Okay. As the load changes. So the radius for the given loading is constant. So E by R can be taken out of the integral sign now. So we can write this as E by R integral y dA. Okay. And what is integral y dA? Y dA is nothing but first moment of area of the beam cross section. First moment of area of beam cross section. Okay. So here dA is elementary area dA and distance of it y. So YdA is moment of elementary area, and integral YdA will be the moment of the total area. Okay, moment of total area lying above the neutral axis and below the neutral axis, above the neutral layer. Okay, moment of area about neutral axis, and that is 0. Okay, so what does this mean is, now the first moment of area for the cross section, which is 0, is that about an axis through the centroid of the section, since this is the basic condition required for the centroid. Okay, so it means sigma y dA equal to 0 says that the neutral axis passes through the centroid of the cross section. Okay, the neutral axis must always pass through the centroid. Okay, it is clear. So to find section modulus, the very first thing is to find the position of neutral axis for the given cross section. Then we came to know what is the maximum distance of the fiber, which is under maximum stress, which is subjected to the maximum stress. Okay, knowing the position of centroid, we will come to know y maximum. Okay, so once you know y maximum and knowing the moment of inertia or second moment of area, we can find the section modulus as I by y maximum. Okay, I by y maximum. This we can find out by knowing first the position of the neutral axis. In other words, position of centroid, because neutral axis passes through the centroid of the section. That is proved. Okay. So how to find the position of centroid? This is already studied. Okay. I am not going to explain that again. So the equation for position of centroid, okay, for different areas, is given as y bar is equal to integral y dA by integral d. Okay, integral y dA by integral dA, or in other words, sigma y dA by sigma dA, or it can also be written as a1 y1 plus a2 y2 and so on, divided by total area a1 plus a2 and so on. Okay, that is sigma ay by sigma a. This is the equation that we use for finding out the location of centroid for any given cross section or compound section, which composes of different areas. Okay, we'll see one by one. Is this clear? Yeah. So now, for strength comparison of different cross sections, we'll use this equation. Okay. Yeah. Here, the strength comparison is done by using the section modulus. The more the section modulus, more will be the bending strength. Okay. Yeah. The higher the value of z, the for a particular cross section, so higher will be the bending moment. Okay. Which the cross section can withstand, which the beam can withstand for a given maximum stress. Okay. So here, as a first example, let us consider a rectangular section. Section modulus for a rectangular section. Okay, which is actually symmetrical about one horizontal axis and one vertical axis. Okay, so we don't bother about this vertical axis. We consider horizontal axis, which is the neutral axis, we call it, because it passes through the centroid. Okay, understand? So let the breadth of beam is b and the depth of beam is d. So here, what is the distance of topmost fiber and distance of bottommost fiber? Being symmetrical, the distance of topmost fiber and bottommost fiber are equal to d by 2. Okay, equal to d by 2. And how about the moment of inertia for this rectangular section? Moment of inertia for rectangular section. Moment of inertia for rectangular section is second moment of area. Actually, it is second moment of area. So you might have studied already in the previous courses. Okay, first I will explain for one cross section how to find the moment of inertia. For that, we consider an elementary area of thickness dy. Okay, so at a distance y from the neutral layer. Is this clear? So what is the elementary area now? The area of the elementary string is breadth is b and thickness is dy. B dy is the area. Okay, and moment of this elementary area, second moment of elementary area, is said to be the moment of inertia. So second moment of area, first moment of area is yda. Okay, so yda into y, this gives the second moment of area, y square d. This is the moment of inertia of second moment of elementary area about with respect to neutral axis. So what will be the total moment of inertia? And the second moment of total area about neutral axis. Okay, yeah, that is obtained by integrating this y square dA between the limits of y. Y is measured from neutral axis, so it varies from minus d by 2 to plus d by 2. Okay, minus d by 2 to plus d by 2. It is clear. So integral y square dA between the limits minus d by 2 to plus d by 2, and dA is here replaced by b dy. So what will be the moment of inertia now? Minus d by 2 to plus d by 2, b y square dy, b y square dy. So b dy is nothing but d. So integral of this y square dy is y cube by 3. So it is b d cube by 3. Oh, sorry. b y cube by 3. b y cube by 3 between the limits minus d by 2 to plus d by 2. So here b by 3 into d cube by 8 plus minus, actually minus of minus, yeah, minus here, minus of minus d cube by 8. So okay, so it becomes plus d cube by 8. So it is b d cube by, here d cube by 8 plus d cube by 8 is d cube by 4. Okay, that is b by 3 into d cube by 4. So the moment of inertia comes out to be how much? bd cube by 12 for rectangle. bd cube by 12. B is base and d is depth. So bd cube by 12 will be the moment of inertia with respect to neutral axis, centroidal axis. Okay? And moment of inertia with respect to any other axis parallel to the centroidal axis can be obtained by using parallel axis theorem. Parallel axis theorem. Okay? Moment of inertia about an axis parallel to the centroidal axis. For example, about base, an axis passing through the base. Moment of inertia can be obtained by using parallel axis theorem. That is, moment of inertia about now axis x passing through the base is moment of inertia about centroidal axis plus ah square, where a is the area and h is the distance between the axes. Distance between the centroidal axis and the axis under consideration. Axis under consideration. Is this clear? Okay. So this way we can find the centroids for all the centroids and moment of inertia for any cross section we can find. Once you find moment of inertia and you know the distance of extreme fiber, maximum distance actually, maximum distance, then we can find the section modulus as I by y maximum. So what is I here and what is y maximum? I is bd cube by 12, just now we have seen, and y maximum is d by 2. So what is the section modulus now? bd square by 6. bd square by 6. So this is the section modulus for a rectangular section. For a rectangular section. Okay? Section modulus for a rectangular section is bd square by 6. Here b is the breadth and d is the depth. Okay? And this is also called as elastic section modulus. Elastic section modulus. And you will come to know this when you know about plastic modulus. Okay? You will understand the difference between elastic and plastic moduli. For now, we call it as section modulus. That's all. Okay? Actually, it is elastic section modulus because the stresses are within elastic limits. Now, second example is circular cross section. Circular cross section. Let us consider a circular cross section of diameter d. Of diameter d. Okay, the diameter d. And consider neutral axis. For this, neutral axis passes through the center because it is symmetrical. Circular also is symmetrical. The number of axes of symmetry are infinite number. You know? For a rectangle, we will have two axes of symmetry. For a square section, we will have four axes of symmetry. Okay, and for a circle, infinite number because any diameter is an axis of symmetry. Okay, let us consider now horizontal diameter, horizontal axis passing through the center. The center and centroid both are same in this case. Okay, it is clear. Now For this, the section modulus, how to find the section modulus. So extreme fiber will be at a distance of radius, diameter by 2. Okay, diameter is d. So the bottommost or topmost fiber will be at a distance of d by 2. So here y maximum is radius, diameter by 2. And how about moment of inertia for a circular section? Moment of inertia for a circular section is, you might have studied, but I'm not going to derive. So its moment of inertia is pi d power 4 by 64. Okay, pi d power 4 by 64. So for this, now the section modulus is given as I by y maximum. I by y maximum, that is pi d power 4 by 64 divided by d by 2. So it comes out to be pi d cube by 32. Okay, these values are to be remembered actually for basic cross sections. The moments of inertia, centroidal distances, section moduli, these are to be remembered. Okay, each time we cannot go on derive, so we better remember these basic things for standard sections. Okay, now let us consider third example: a square cross section with its diagonal horizontal. Okay, a square section with its diagonal horizontal. Okay, so here the centroid will be the point of intersection of the diagonals in a square. So neutral axis is the line passing through the centroid. Okay, understand? So neutral axis is here horizontal. Okay, passing through the diagonal, horizontal diagonal. Now let the side of square be a. Side of the square be a. So what will be this diagonal length? Total length of diagonal, it is root 2a. Okay, length of diagonal is root 2a, and extreme fiber distance, topmost or bottommost, will be half of this length, root 2 by a divided by 2, that is a by root 2. So y maximum is a by root 2. Y maximum is a by root 2. This clear? And how about moment of inertia? How about moment of inertia of this? If you know the moment of inertia of triangle about the base, then base B and height h. For a triangle about base, the moment of inertia is BD cube by 12. Okay. About centroid, it is BD cube by 36. Okay. So about base for a triangle, uh, height is h and bh cube by h in place of the, let us take h, height of the triangle. So bh cube by 12 is the moment of inertia for a triangle about base. Okay. So in this square we have two triangles. One is above neutral axis with base. What is the base of this triangle? Nothing but the diagonal length. Base is the diagonal. Okay. And how about the height? Height is a by root 2. It is clear. So you have two triangles, one above, one below. So the moment of inertia is both are of same dimensions. Okay, base is same and height also is same for both the triangles. So moment of inertia is 2 times bh cube by 12. What is base? Root 2a, and h is a by root 2. bh cube by 12. This is for one triangle. So for two triangles it is multiplied by 2. Okay. So moment of inertia is now, so it is a cube by 2 root 2 into root 2a. So it becomes 2 by 12 means first it is 1 by 6 into root 2a, this one, into a cube by 2 root 2. Okay. So root 2 gets cancelled. So you will have a power 4 by 6 is the moment of inertia for a square section with diagonal horizontal. With base, with the side horizontal, what is the moment of inertia for this? With side A, what is the moment of inertia of square section with base horizontal, with one of the sides horizontal? It is just like rectangle. So BD cube by 12. So A into A cube by 12. That is A power 4 by 12 is the moment of inertia with one of the sides horizontal. With one of the diagonals horizontal, the moment of inertia is a power 4 by 6. It is a power 4 by 12 for square with one of the sides horizontal. With one of the diagonals horizontal, the moment of inertia is a power 4 by 6. A power 4 by 6. Okay, and y maximum is a by root 2. Y maximum is a by root 2. So the section modulus is I by y maximum. So I value is a power 4 by 6 by a by root 2. So it is a cube by 3 root 2. A cube by 3 root 2. So this is the section modulus for square section with diagonal horizon. And here for square section with side horizontal, so what is y maximum? A by 2. Y maximum is a by 2. So I is a power 4 by 12. So what is the section modulus in this case? Section modulus for a square section with one of the sides horizontal is I is a power 4 by 12 divided by a by 2. That is a cube by 6. A cube by 6. Okay. A cube by 6 is the section modulus for square. Yeah. With this, I will end the session. Let us discuss some more sections in the next class. How to find the section modulus and moment capacity. Most important, moment capacity of the cross section also we'll see. Okay. Yeah. For now, let me conclude this. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.